Welcome. In this third and final video on Verilog, let's talk about parameterized modules and parameterized testing. So sometimes it's useful to parameterize models. What I mean by that is based on user input or based on the way by which you're using a particular module, you want to change its word input or its word output, right? So you want to convert something from 2-bit to 4-bit. The logic is essentially the same, it just means that it's accepting different input vectors. So it sometimes helps instead of rewriting these and creating multiple modules, just create one parameterized module and pass the parameter through it, and it will automatically generate the module with that required number of bits. Right? For example, let's look at a very simple 2:1 MUX, right? Where what we want to do is we have two inputs and a single output. And so we want to select between one of the two inputs using this logic variable, which is the select variable S. Right? So previously we've written the MUX behavioral model. You've given an input signal, an output signal, and a select signal, and then we use a conditional assignment here saying that depending on the value of S, you either assign the output to D1 or to D0. Now what is different here is we're using this keyword in the Verilog code, and that is the hash parameter. So when you declare this as a hash parameter, that is basically telling what follows subsequently, like in this module, it's telling that you have this parameterized variable which is width, right? And I'm using this width as an variable to vary the input word length. So when I'm using this and then I instantiate that width, so for example, I'm saying that parameter width is equal to 8. This means that what I'm saying is that by default, right, I assume that it is an 8-bit input. Now, obviously, we'll see how this can be changed later, but here I'm declaring that this Verilog module is parameterized with a variable known as width whose default value is set to 8. And based on the value of width, the input word length would vary. So the input word length goes from width minus 1 to 0, and the output word length goes from width minus 1 to 0. So now let's see how we can instantiate this. Now typically the way we would run it previously, the way I would instantiate, suppose I want to build a 4:1 MUX from this 2:1. So basically my select now becomes a 2-bit word, and so I have 4 inputs D0, D1, D2 and D3. So I'll use 3 2:1 MUXes to create this large MUX. So I'll use 2 MUXes in the beginning. Based on S0, it's going to select either D0 and D1 or D2 and D3. And then S1 is used to select between the outputs of the 2 MUXes, capital M1 and capital M2. Right? Now here, when I'm instantiated as this without any particular hash here, by default, this is going to be instantiated as an 8-input MUX, right? So here, because we had initially set parameter width is equal to 8, when nothing is mentioned here, it automatically assumes that this MUX2P is an 8-bit input and an 8-bit output, 2:1 MUX. Now suppose I want to convert this to a input which has say 16 bits as an input instead of the 8 bits, right? So again, I'm not going to write a new piece of code. I'm just going to use my parametric version. So what I would do here is, again, I define this MUX416, right? And that has an input of 4 words, each of length 16 bits, a select signal which has 2 bits, and an output signal which has again 16 bits. And I'm declaring the internal variables used in the Verilog code to be capital M1 and capital M2. So logic remains exactly the same between the two. Now what we do here is we instantiate a 16-bit input MUX using this phrase here, MUX2P hash of 16. When you use this instance hash of 16, it uses the parameterized version of MUX2P. So it's saying that instead of using it as an 8-bit MUX, use it as a MUX in which the value of width is taken to be 16. So now when this is instantiated and when you run this code, you're going to be basically replacing, this is going to create a 15 or a 16 input MUX and another 16 input MUX here. Right, so the same thing, all we've done is by identifying the width parameter, by passing a parameter through this instantiation, you're able to convert the same code to a 16-bit code. Now, MUX was a simple example, but again, so you see here that just writing one code for a MUX 2:1, I can use it to create or functionalize any length word inputs. Now, another useful case where we use this kind of parameterization very commonly is in a decoder. Now, a decoder, if you think about it, depend as the number of bits in the select word increases. Now, what does a decoder do? A decoder converts an n input to a 2 power n output, right? So now you can see that very quickly, if I'm going to behaviorally code this piece of hardware, as my value of n increases, you're going to see that I'll have to write the code for 2 power n. And if I even if I use case statements, my case statements are going to increase. So a simple way instead to do that would be to parameterize the decoder. So here's a example of a decoder that is parameterized. And again, I'm passing a parameter term and setting its default to be an 8-bit input. So my input logic is a 8-bit word, logic n minus 1 to 0 of s. And my output logic is going to be 2 star star n. Now this 2 star star n is basically 2 power n. So my output logic is a 2 power n minus 1 word, right? And so the simple way to set a decoder is use the always statement. So I have it always at comb, initially set all of it. So again, remember here, in always we use blocking assignments, we don't use non-blocking. So in a blocking assignment, I initially set all my outputs to 0, and then based on the value of the input word, I set my d of s to be 1. Now remember, this advantage of Verilog comes in because Verilog by default will treat this as a decimal. So what you see here is d of s immediately will raise the asset output bit to 1, right? And so this is a simple way. So now here, because I parameterize this, I can quickly use this as a 2:4 decoder or a 3:8 or a 4:16, whatever have you, by simply repeating this code and only passing a different parameter through its input, right? Now, another useful statement in Verilog, just like how we have the parameterized statement, is a generate statement. And what a generate statement is used is it's used to generate hardware, right, based on the user input. So let's look at a very silly example. For example, suppose I have 2 input AND gates and I want to generate an n input AND gate based on this 2 input AND gate, right? So how would you do that? So very simply what you do is you'll take the first lowest 2 LSBs at one time, AND them, take the output of that and AND it through bit number 2, again take the output of this, AND it through bit number 3, and so on and so forth. So what you see is that you are basically doing a succession of multiple ANDs. So you're ANDing 2 at a time, taking the output, ANDing it with the third. So you see that there is a recursiveness happening here which can be coded. So the way you would code this here is shown here. Again, this is again generating hardware that is user defined, right? So for example, here I'm generating by default an n bit and the way I do it is I'll define my input logic to be a 7 input word. My output logic is a single output z, which is going to be the AND of all the bits in A, and I'm defining a variable which is going to be used for my generation. And this is an internal variable to the module, and this is known as genvar j, and I'm defining an internal array. So every output of the AND I'm pushing it into an array, and again this is an internal variable to the module. It's again parameterized, so I have logic of n minus 1 0 to be x, right? So this x holds the intermediate outputs of the various AND gates. Now I use the keyword generate. So now this is now generating the hardware. And how do I generate the hardware is first I assign the output, if you will, of the first AND to be some a of 0, and then I loop j, that is the gen where from 1 to n, and in the for loop I assign x of j to be a of j ANDed with x of j minus 1. So I take the output of the previous AND gate, AND it with the next variable, and give the output to the output of the AND gate. And so when I'm doing this, what I'm generating is I'm basically creating an n input AND gate by ANDing the outputs of every 2 bit together, right? And so when you use the generate command, we have this we have a for statement, and then you have this begin, and this is a label. We normally have, especially in the latest Verilog's version, you need to have a label for this begin loop, right? And so once this is done, you indicate the end of generation by using the keyword end generate. And then you know that finally you want to set the last output of the AND gate to be the output of the module. So you assign Z to be X of n minus 1. Right? So this is how you generate a simple n input AND gate out of a 2-input AND gate. Now you might ask, okay, this is silly. You could have directly written this as an AND of all the bits together, right? I mean, using bitwise functions, we could have done that. So this is just to show you the idea. Now, another powerful circuit where this can be used is for an n-bit adder, right? So I can now basically have a parameterized version of an ALU, for example, right? Because I can now discuss, for example, how do you want to do a study on, say, what happens to the microprocessor as you change the number of bits in its word, right? And you want to see what effect it has on delays, what effect it has on speeds, etc. So in that case, you might want to generate elements which basically you want to generate as a function of the input bits. So for example, to generate an n-bit adder, a simple way would be is you first create a full adder, and a full adder, as you all know, takes in 3 inputs A, B, and C in, and provides 2 outputs, sum and C out. And we assign sum to be the XOR of the 3 inputs, and C out is going to be the max function of the 3 inputs. So it's A and B, or B and C, or A and C, right? So this is a full adder that's been generated, right? And what I now want to do is I want to cascade. So this is like a very simple ripple carry adder where I'm now going to add the LSBs, push the carry to the next significant bit, and so on and so forth. So the way I would write this again is I'm parameterizing this code. So I'm saying, okay, I'm now creating an n-bit adder, where the parameter by default is set to be 4, and I'm defining in 2 of the input words. So I'm adding 2 n-bit numbers, which are shown here as n minus 1 to 0 of A and B. I have an input carry, and I have an output sum, which is again an n-bit sum, and an output carry, right? So these are the inputs and outputs of the module, which is parameterized using this term n. So again, I declare a generate variable. I declare an intermediate. Now this is your carry, right? This is an array which contains all the carries that are happening between the different full adders, right? Or a bitwise addition. So now I create a generate loop, and I assign the first carry of the LSB to be C in. And then what I do is I'm generating n minus 1, or rather I'm generating n full adders, right, one at a time, where I take the full adder and I pass the jth bit of A, jth bit of B, the carry of the previous adder, and the outputs are nothing but the sum at the jth bit, and I send the carry of the next. The C out of the jth adder becomes the carry in of the next adder, right? So this is similar to the AND gate, but this is a very useful code, because now I've basically instantiated n full adders to simulate this bitwise addition. I then do an n generate, and then the output of the last full adder, which is carry of n minus 1, that I assign it to C out of this n bit adder, right? So now this is where generate helps, right? Now the key you want to keep in mind with using generate is, while generate is powerful, you can have a tendency to create circuits which are very large if you let this generate run uncontrolled. So you have to be wary that eventually you're writing Verilog code for hardware. So there are practical limitations on how much hardware you can stuff between, say, different clocks, right? So be very careful, because there is a propensity to generate useless hardware if you use the generator, right? So that even though you might be thinking that you're doing an optimization, it might end up that you're creating junk hardware. So while the generate term is useful, use it with care. Now the last part of Verilog I want to talk to you about is a test bench. Now what's a test bench? So a test bench is nothing but a program that is used to test your module. And we do that by calling the module, and that module is known as a device under test. So I instantiate a module and call it a device under test. And then what I do is I apply inputs to this DUT and I check the outputs. And I make sure that the outputs are in line with what I'm expected them to be. And if that is true, then I say that the test bench is passed the module, or I can flag which are the inputs that it doesn't give the right outputs and go back and debug my circuit. Now, just keywords is that the input and output patterns are typically known as test vectors. So you use that word often. Now, what does a typical test bench contain? A typical test bench instantiates the device under test and then applies inputs. We normally use blocking assignments and delays to apply inputs in appropriate order, and then the user can view the results and assess the correct outputs are produced. Now, a much better approach, instead of making the user view the results and inspect the output, is to create what is known as a self-checking test bench, where the test bench by itself, you pre-program it to check the outputs and flag if there's any discrepancy between the expectation and reality. Another very efficient method, which you'll use a lot as you build larger circuits, is to use files where you put in all your test vectors and you let it rip on a particular module. So I'll give you a couple of examples of both. Now, one thing, as I mentioned previously, remember that test benches are not synthesizable. So there is no hardware equivalent of a test bench. A test bench purely is used primarily for what it stands for, testing a design. Now let's look at a very simple, silly example of a test bench, right? Say I have some Verilog module I've written, which is some module to test, right? So this module to test is a module I'd like to test. It takes in 3 inputs and an output. And so I can call, so I'm referencing a module which is a test bench. I'm declaring the logic variables in it, A, B, C, and Z. I'm instantiating the device under test. So the module to test is the module, and DUT is an instantiated version of that Verilog module. And then I have the statement which is initial begin, and here I'm doing. So once I've instantiated the device, now I have to send in inputs, right? So now the initial statement, when I use something like this, is basically done at the start of the simulation. Now in this case, I don't really do anything beyond it. All I'm doing is, if you pay attention carefully, I'm sending the input word from 0 all the way to 7 and seeing what the output is, right? So I start with ABC0, and then this hashtag 10 is basically saying that after 10 units of time, this transition occurs. So initially A is equal to 0, B is equal to 0, C is equal to 0. Then after 10 units of time, C flips to 1. Again after 10 units of time, both B flips to 1 and C flips to 0. And so on and so forth. So what you're doing here is this hash 10 indicates a time variable, and it's showing after what time these inputs change, right? So as I mentioned, the input cycle from 0 to 7 every 10 time units. So here's how I would convert the previous code into a self-checking code, right? Now what's the advantage of a self-checking code? The advantage of self-checking code simply makes it easier for you as a designer to check your test benches. And the reason is because whenever you do a design fresh, you have your mind space where you know clearly what the outputs are. But say you're looking at your design in 3-4 days, then it's possible that you don't remember the exact way the design functions. So it's always a good idea to write the test benches with proper outputs written in. That way you can always run the test bench and verify the design as you keep changing the design. So the way one would do it is use what are known as these assert statements. And what the assert statement does is right here. So once you declare the variables, you declare the DUT, and you start A0, B0, C0. And then what you're doing is essentially checking. So this assert statement checks if the condition is true or not. And if it is not true, it's going to give you an error saying that the input 000 failed, right? So here what you're using is this Z equal to equal to equal to. Now this equal to operator is important because it's used for comparison, especially when you have the don't care or the tri-state conditions. So you can use the double equal to operator too in this code, but the triple operator is a superset, and so generally I use that. Now let's see how to write a test bench where you have defined test vectors in a file, right? So suppose you have to do multiple, you want to check multiple test vectors on a given design. So it's normally helpful to type in all the test vectors that you want to check along with the expected values of the output in a file, and then read off it and let the Verilog handle the testing. Right, so here again, this is a sample code where I've started off with defining the test bench with all the inputs. I have a couple of internal variables designed which are pointing to the vector number, that is which test I'm doing. I have a variable which is going to count the number of errors my design generates. And then I as usual, I instantiate my device. And then here's how I define a clock, right? And so again, this is an example where you have a clock which has a time period of 10 time units with a duty cycle of 50%, right? So that's what this statement is doing. And then what we're doing is we're reading off this file. So this .tv file includes all the test vectors. So we use this function known as readmemb, which reads this file in binary format. It's telling you that the data is in a binary format. And the way it is given is these are the input variables and this is my output, right? So I give it as a 4-bit word and separated by a new line column. So again, I've initialized my internal variables, the vector num and errors to 0. And I'm just testing this for 30 time units and then I'm resetting the device. So the way this would now work is, what I'm now going to do is I'm going to, at every clock edge, I'm going to apply the inputs and I'm going to check for the output at the falling edge of the clock, right? And so the way I do it is at the positive edge of the clock, I'm giving some small time instant just to ensure that the clock edge is separated from when the data is coming. Again, this is just for my clarity. You could have as well mentioned it next to each other, not an issue. And I'm saying that A, B, C, Z expected is read off this test vectors file. So this test vectors column contains all the test vectors that you've read from your file, right? And so one by one, you're going to pass through them and select them one by one. So the first thing is you load up the first vector into A, B, C and expected value of Z. And now at the negative edge of the clock, you check if reset is on or off. And if it is not reset, then what you're going to do is you're going to check if Z is equal to Z expected. And if not, then you're going to begin and display the errors, right? Once that is done, then you update your vector number. So you move on to the next text vector and so on and so forth. So you continue this until you exhaust all the test vectors. And how do you check that you've exhausted all the test vectors? Is basically you use this test condition that you say when the test vectors of vector num point to 4-bit of x. X is essentially not defined. Then essentially that is telling you that the test vector file is complete. And so you say that the test has been completed and you quote the errors that you've got. Now again here, like C, you have the %B and the %D, which help you display the output either in binary or in decimal format. And finally, use this keyword $finish to terminate the simulation. Once you've done that, then you can close up all the modules and if statements and for statements that you have opened. Finally, I hope you've gotten a sense of Verilog coding from this video and the previous two videos. So just a few points to remember. HDL that used for simulation and synthesis. Simulation is a powerful way to test a system before it is turned into hardware. Synthesis is the next step and that converts whatever you've coded up in the HDL into digital logic. Now, one thing to remind yourself every time you do Verilog coding is you're not coding in Python, you're not coding in C. You're coding for hardware. So if it's important that when you're coding this up, that you have an idea, what is the hardware you intend to use? It's very hard to write Verilog code without an idea as to what the hardware is going to be. And finally, because this is a design exercise, it's useful to start your design initially with block diagrams. identify which of the parts are going to be combinatorial, which of the parts are going to be sequential, create these individual modules, test the modules, and then start putting together. Just like how you write any large piece of code, break the codes into smaller modules, test those modules. Once you're satisfied with them, then you start building bigger and bigger modules. And then once you know how to write test benches, you can then validate your design to ensure functionality.